Okay, we're going to take a look at the absolute and maximums and minimums of a function and the relative max and mins or local max and mins for functions. And so how do we find that? It's real important given a function to be able to what we call optimize the function, find its extreme values or its maximums or minimums. And so we want to clarify what we're talking about and then show the calculus in doing that. So we first of all talk about the absolute, sometimes called global extreme values or extrema is plural. And so a function has an absolute maximum or just a maximum at a value of x equals c if f of c is greater than or equal to f of x for all x in an interval of the domain of f. So for all values of the function in the given interval, and the interval may be the entire domain of the function depending on what we're talking about, but on whatever interval we're talking about, we're going to say that we have a maximum at, right, the value of the input or independent variable x when it's c, if the value of the function at c is greater than or equal to all the other values of x in that interval. So that kind of makes sense. So the f of c is the maximum value on that interval. And so f of c is indeed called that, the maximum value of f on this interval. Similarly, we can define an absolute minimum or just minimum for a function, and in that case the value of the function at the point x equals c is less than or equal to f of x for all x in that interval. The maximum minimum values, as I said, are called extreme values or extrema. Singular would be an extremum, like a minimum or maximum. We've got extremum. Now, a function may not have a maximum or minimum value on a given interval. For example, the function below has a minimum value of -1, right? The value is the output, right? The y value, the range value, at x equal 1. But it has no maximum value, right? Because this is going to continue opening upward in both directions, right? So we will not have a maximum value. So the other type of extreme values we want to talk about are relative or local extrema. So here we're going to consider a maximum or minimum over a small open interval of the function's domain. So in that case we will say f has a local or a relative maximum at x equals c if f of c is greater than f of x, greater than or equal to f of x for all x on that open interval. And in that case f of c is a local maximum. Similarly, we have a definition for a local minimum then, right? If for all values in that open interval, all values of x in that open interval, f of c is less than or equal to f of x, then f of c is a local minimum. So here's an example of what we're talking about. Here's a function, and assuming this continues in this pattern, this is going to continue to go down as we move to the right. As we go to the left, it's moving up. So the range seems to be all real numbers, so we'd say, well, there's no maximum or minimum. But it does have actually many local maxima and minima. And so the ones we can see here, notice we have a local maxima of about 1.8. We're looking at right at this point. The height of that function right in here is about 1.8. At x equal about -1.25, somewhere about right there is our location. Notice how we write that. So what we're saying is on some open interval about -1.25. So if I just restrict everything in between the two pens, just look at that open interval. And by open, by the way, what do we mean by open interval? This means excluding the endpoints. So everything strictly between these two pens, right? Then the value of the function f is at about -1.25 is greater than or equal to the value of the function at any other point in this interval only, in between these pens. Now clearly, if we move outside of this interval, like if I go over here, functional values are getting bigger than 1.8 over here, clearly. But locally, right, we have a maximum there. Similarly, we have a local maximum of about 0, right at about x equal to about negative 3.1, oh, that was min. Yeah, local maximum of 0 about x equal about 3.2 is what I'm saying, yeah, right about there. And then we have a local minimum, as we said, at 0 at about x equal negative 3.1, and then also a local minimum of about negative 1.8 here, right? That's the y value at about 1.25. Okay, and if the trend continues, we might have an infinite number of local minima and maxima in the situation, but the ones that we see in this window are here. So again, there's no absolute max or min for this function on its domain, but there are local max and mins. And so we're going to be looking at finding both types, both absolute max mins on a, or global max mins on a set interval. Maybe the domain of is all real numbers, or maybe some closed domain. By closed, I mean including the endpoints. But if we're talking about a max or min on an open interval, right, then we're talking about the local max or mins for the function. And so we want to look at both of these. We're actually going to focus on the absolute max and mins in this section 4.2, and then we'll talk more about local max and mins in the coming sections, how to find them. However, we are going to be using local max and mins in a sense in talking about how to find absolute extreme values, because if we have an absolute extreme value, then it has to also be a local extreme value. So for instance, this absolute minimum of -1 we talked about that occurred at x equal 1, that's also a local minimum. That's also a local minimum. So if you have an absolute max or min on an interval that's open, I better be careful about that, because I might just contradict what I just said, because on a closed interval, we'll see here in a minute, then we can have a max or min that occurs at a location other than a local extreme value. But in this case, yeah, this is also a local extreme value as well. Okay, so let's take a look at an important theorem. And so I do want to focus on closed intervals and finding extreme values on closed intervals here, because the extreme value theorem talks about that. It says if f is a continuous function on a closed interval from a to b, then the function f has an absolute maximum of f of c and an absolute minimum of f of d for c and d both in that closed interval. And the extreme values that we have here may occur more than once. So let me illustrate this. You know, the key is that the function is continuous. That's a key part of this. Remember what it means for a function to be continuous. Right? The limit exists at every point. The value of the function exists at every point, and those values are equal to each other at every point in the interval. So let's say from a to b, a being the lower left-hand endpoint, if you will, of this closed interval, and b being the right-hand endpoint. So if I were sketching a function, you know, and I said, okay, the value of the function at a is, you know, right here, and the value of the function at b is right here. Okay, could you draw a function, you know, connecting these 2 points, that is continuous, that doesn't have a max or min? And this theorem says no, you can't. Okay, well, can you draw a function that's, what if the function is not continuous? Well, then yeah, I can draw it in such a way that it doesn't have an absolute max or min. You know, so an obvious example could be that I draw a function maybe like this. I come up to this point, and then I drop down Okay, so obviously this function is not continuous on the interval from a to b. Now we do have an absolute maximum, right? If you think about it, the y-coordinate of this point, that's the highest possible y value we have. Okay, so we have an absolute maximum. Now, what's happening down here, right? Open circle means there's no point there. Now, someone might say, we have a minimum value. Well, this point's not included. So, I mean, the minimum is not, whatever that's at. Let's just suppose that value down here, just sort of make this up here as we go. Let's suppose that value is, I don't know, -2. Okay. And so, it can't be -2 as our minimum. So someone says, well, just pick the number that's the next biggest number. What's the next biggest number that's bigger than -2? What's the next one going up? And there's where we have a problem, because the answer is there is not one. We kind of had a talk about this, if you remember, a while back at the beginning of the semester, but there is not a large, a real number, a smallest real number that is bigger than -2. Someone might say, well, it's, -1.9. That's certainly bigger than -2, but there's a number bigger than -2 that's closer than -1.9, right? Namely, -1.99. So is that the largest number? Smallest number larger than -2? No, because I can go to -1.999, right? And so how can you can continue this process, right? Until you get to what? -1.999 repeating. Sometimes we write it this way. And someone would say, that's the number we're looking for, right? Well, without talking much about this, I don't want to confuse anybody too much, but this number is -2. And I can prove that to you. You can come during my Zoom session and we'll talk a little bit about that. But it is actually the same thing as -2. Bottom line is we don't have a minimum value for this function on the interval from A to B. Okay. Another way we could have drawn it is we could have had a vertical asymptote, right, where I was approaching infinity from both sides at some vertical asymptote here, and clearly that function, right, would not have a local max or min. Let's just draw that. So, for instance, there's another way I could have a function on the interval from A to B that is not continuous. And let's suppose we do this, and well, let's just bring it down this way. What the heck? Doesn't really matter which way we go. There's no maximum value, right? This continues to go up forever, approaching this vertical asymptote, and going down forever, approaching that vertical asymptote. And so there is no max or min. So up here we have a max, no min. Here we have neither max nor min on the closed interval. However, if again I force the issue and say you must be continuous, then if it is continuous, I can't have this situation, right? Because the limit doesn't exist here, right? The limit from the right and the limit from the left both exist, but they're not equal. Here, the value of the function doesn't even exist, and the limit, right, doesn't exist either, so we're not continuous. But if I force the issue and say I have to be continuous going from A to B, then I can't have any holes, gaps, jumps, vertical asymptotes, anything like that. So, where can I go? I try and move away and try and do something crazy, but, I've got to come back to there, and therefore I have what? There's your maximum value up here, and I have what down here? I have my minimum value, okay? And that's one way we can have a max and min occur. You can also have a situation, say from A to B, something like this. Let's do B a little bit down here. And I can drop down here below and come back up. And now I'll notice our minimum is down here. There's our smallest y value. What's our maximum y value? It's actually right here at the end point. And so notice I was talking about a little while ago for absolute max I almost mistakenly said that absolute max or min has to occur at a local max or min, or an absolute maximum or extreme value has to occur at a local extreme value. And that's not true. Right here we have a local minimum and an absolute minimum, but here we don't have a local maximum. Right? We have an absolute maximum. Right? Because we would have to have a closed open interval rather to talk about a local maximum. And the question is, what's going on for this, for the function beyond, for values less than a. We have to bring that into the picture. And so we're going to see when we're finding max and mins on closed intervals that they're going to either occur at local extreme values or at the endpoints of the interval. So we're guaranteed, though, to have a max and min if the function is continuous. If it's not continuous, then we're not guaranteed. So that's the extreme value theorem. Now, in order to help us in the process algebraically, so what we're going to go to find max and mins on a closed interval, we need to talk about critical points, and that's what I want to finish this video up about, talking about critical points. Okay, so a critical point or number for a function is a number C in the domain such that either the derivative is equal to 0 or the derivative does not exist. Okay, so I want you to think about, the derivative equaling 0. You go back to the graphs that I was drawing, you kind of know where the derivative is 0 for this function, right? It's right there at the maximum, right, where the slope of the tangent line would be horizontal, or would be 0, or a tangent line is horizontal, right? And then down here at the minimum, we would have a horizontal tangent line too. So you can see why those are critical points, because they're going to help us potentially find the max and mins. What about when we're talking about where the derivative does not exist? Do you remember where that can occur? That can occur, remember, where for instance, you have a sharp turning point, right? And so another thing that could happen from A to B, a continuous function could look something like this, right? I've got a sharp turning point there, and clearly I've got a minimum here, right? Minimum here, and I don't know, maybe here's our maximum up here. So we're guaranteed to have a max and min. And that sharp turning point, the derivative there, though, is undefined. Okay. We can also have derivatives at that are undefined when we have a vertical tangent line. Okay. But so the critical points have something to do, if you think about it, with possible locations for absolute max and mins on a closed interval, and that's where we're going. But let's just do the actual exercise of finding critical points. So how do we do that? So I want to find the critical points for the function p of x. So what do we do to find the critical points? So first of all, note that a critical number is a value in the domain of the function. So we need to know what the domain of the function is when we start off. What's the domain of this function here? It's a polynomial, right? Domain's all real numbers. Have no problem with any value of x going into that function. What do we need to do to find critical points or critical numbers? We need to find the derivative. So what is the derivative of this function? Well, that's pretty easy, right? By the power rule, we get that. And now what I like to do is to go ahead, I'm going to be looking for when this is 0 or undefined. I like to go ahead and factor this expression. All right, and then notice I have what? Difference of squares there, so I can completely factor this way. Okay. So what are our critical points? Well, the derivative is going to be 0 when x is equal to what? Either -1 or +1. Plus or minus 1. CP's will be my abbreviation for critical points. And those are my critical points. Notice there's no values of x that make the derivative undefined. This polynomial function, the derivative is defined for all real numbers. Okay, so that's pretty simple for polynomials. Basically finding the derivative, and then finding the values of x that make the derivative 0. Now let's take a look at this function. This function is not a polynomial function because the exponent here is not a whole number. Realize that x to the 3/5 power means, the fifth root of x cubed. Fifth root of x cubed. What's the domain of this function, though? Well, when I take the fifth root, can I take the fifth root of any real number? Both positive and negative numbers? Yes, I can. For instance, the fifth root of negative 32 is negative 2, because negative 2 to the fifth power is negative 32. So the domain here, again, is all real numbers. All right, so what rule will I have to use to find the derivative for this function? Well, I've got what? A product, so I have to use the product rule. Well, technically you could distribute this through and not use the product rule, but I'm going to go ahead and use the product rule. The derivative of x to the 3/5 is 3/5. X to the what? Subtract 1 from 3/5. It's negative 2/5 times 4 minus x plus x to the 3/5 times the derivative of 4 minus x, which is what? Negative 1, right? Derivative of 4 is 0. Derivative of x is 1, so 0 minus 1 is negative 1. And so what can I do with this expression? Well, just like above, what did I say? I'd like to factor. I'm going to factor. Now, you can, of course, with negative exponents, you know how to rewrite this as 1 divided by x to the 2/5. And you can actually write two fractional expressions, and you can find a common denominator and add them or subtract them, as the case may be. But I'm going to factor, and I'm going to factor out something that you might not think to factor out here. The coefficient here is 3/5. Here it's negative 1 or 1. And you might say, well, there's no common factor. I'm going to factor out a 1/5. You say, how in the world are you going to... I see how you factor out a 1/5 out of this. How do you factor out a 1/5 from here? Well, we'll talk about that here in a minute. X, I can factor out. I've got x to the negative 2/5 power, x to the 3/5 power. What do I factor out? Again, you can factor really anything you want to out, but what we like to do is what? Factor out common factors. We pull out the factor with the lower exponent, the smaller exponent, I should say, smaller exponent. So which is smaller, negative 2/5 or 3/5? Negative 2/5 is clearly smaller. That's what I'm going to factor out. Okay, so let's see what's left from this first term. I pulled out a 1/5 from 3/5. That's going to leave me 3. I pulled out x to the negative 2/5. Well, there it is. And what am I left with? 4 minus x. Okay, so if I multiply this stuff here times this stuff here, please understand that you get this stuff here. Right? Now what do I have over here? Well, I have a negative 1. Negative 1, but I've pulled out of that a 1/5. How do you do that? How do you pull out a negative 1 or 1/5 from a 1? Well, 1/5 times some mystery number equals 1. What goes in here? 1/5 times what is 1? Answer 5. So that's what's left, 5, right? I'm left with a 5. 1/5 times 5 is 1. Now, here's the other question. I pulled out x to the negative 2/5, so what do I have here? X to what power? Well, when I multiply this x to the negative 2/5 times x to some power, what do we do with these exponents? We add them, right? So if I have negative 2/5 and I add something to it, the exponent here, right? What am I going to get? 3/5, right? So x to the negative 2/5 times x to some power is x to the 3/5. And what goes here? How do I go from negative 2/5 to 3/5? I add 5/5 or 1. Right? So that's just 1. And that's what the exponent is here, 1. Okay. So I hope you see now why I factored this fraction out and this, because This right here now can be simplified, right? Distributing the 3 and then combining like terms, I get 12 minus 8x. And I can even factor out of that what? A 4. And so the bottom line is, what do I have? This, of course, becomes what? 1 over x to the 2/5, right? So I'm left with, up top, 4 times 3 minus 2x over 5 times x to the 2/5. Right? And so from that, what are our critical points? Critical points are where the derivative is 0 or undefined. Okay. When is this expression going to be 0? Well, when the numerator is 0 and the denominator is not 0. That's how we get 0. So 3 minus 2x equals 0 when what? When x is equal to 3/2. Right? So when x is 3/2, the derivative is 0. But notice, someone might say, well, isn't the derivative 0 when x is 0? Well, no, it's not. If I plug in 0, I get 12 divided by 0, which is undefined. Right? 0 is in the domain of the function, but we want to include that as a critical point because remember, critical points are what? Where the derivative is 0 or what? Does not exist, is undefined. So the derivative does not exist at 0. Okay, we'll do 2 more examples. So here we're going to deal with some trig functions. Some sine and cosine. What's the domain for this function? Well, the domain of sine and the domain of cosine is all real numbers. So again, domain is all real numbers. So what do we need to do? We need to take the derivative. Okay. Well, derivative of each part, derivative of sine of t is what? Cosine of t. What's the derivative of cosine squared t? Well, be careful. This is a composition, right? This is cosine of t all squared. So we've got the chain rule going on, right? I guess you could turn it into a product rule, but we can do a chain rule, right? We've got outer function is u squared, inner function cosine t. So the derivative of the outer function, bring the 2 down to the first power, right? Times the derivative of the inner function, derivative of cosine, negative sine of t. So this part here, right, is chain rule. Okay. And so notice I can do a little factoring. There's a common factor of cosine t, and that's what I'm going to do. I'm going to factor that cosine t out, and that leaves me 1 here, and what? 2 times negative 1, negative 2 sine of t. So the derivative, notice, is never undefined because this the sine and cosine function, again, have a domain of all real numbers. But the derivative of our function will be equal to 0 when what? Either cosine of t is 0, right? Or this is 0, right? So I've got the product of 2 things. They will be equal to 0, right, when one of the 2 things is 0. So when is cosine of t equal to 0? Well, think about our unit circle, right? The x-coordinate, right, is cosine of t as we move around the unit circle. The x-coordinate is 0 is up here at pi over 2 and down here at 3 pi over 2. But that's just on the interval from 0 to 2 pi. Right? That's just on the interval from 0 to 2 pi. Notice there's an infinite number of values, right? Because I can go add pi to any of these values and get to another one. So I can go pi over 2 to 3 pi over 2. I can have pi more and get to what? 5 pi over 2, 7 pi over 2. Or I can go back to negative pi over 2, negative 3 pi over 2, negative 5 pi over 2. There's infinitely many. Do you remember how to write that? T is equal to, well here, notice that they're all pi apart, right? I'm always pi apart from one another. So it's just pi over 2 plus n pi, right? Where n is any integer. There are infinitely many critical points. When you think about sine and cosine, right? They're going up and down. You can imagine there's an infinite number of times where that derivative is going to be 0. Okay? What about here? Sine of t is equal to what? If 1 minus 2 sine t is 0, then sine of t has to be equal to 1/2, right? 2 times 1/2 is 1, 1 minus 1 is 0. So where is sine of t equal to 1/2? Well, you should be able to look on the unit circle or know it occurs at pi over 6. But what other location? Remember, it's the y-coordinate, so it's also positive what here in the second quadrant. Same reference angle, pi over 6, so this is 5 pi over 6. Now, here, pi over 6 to 5 pi over 6, that's just 4 pi over 6 difference going from here to here, or 2 pi over 3, right? But 5 pi over 6 all the way around to technically 13 pi over 6 is 8 pi over 6, or 4 pi over 3. So it's 2 pi over 3, 4 pi over 3. They're not the same distance apart as pi over 2 and 3 pi over 2 are. So in that case, right, we would have to write that t is equal to pi over 6, and I can go all the way around. What's that? 2 pi. And again, 2 pi, and I'll be right back there. So plus 2 pi, or 2n pi. Or t can be 5 pi over 6 plus 2n pi. Now, a lot of times when we're dealing with trig functions, they will say give the critical values for this function only on the interval from 0 to 2 pi. Let's say only on the interval from 0 to 2 pi. In that case, what would our critical points be? They would be pi over 6, pi over 2, 5 pi over 6, and 3 pi over 2. So a lot of times we'll restrict the domain, say just on this interval. And because of the periodic nature of the trig functions, a lot of times that's sufficient to be able to talk about what's happening. But we do have, in this case, all these critical points. All right, one more example. Let's take a look at the function h, and let's give the domain for this function. Again, the function exponential functions, right? E to the 2x, any exponential function has a domain of all real numbers again. We're just multiplying by x. We don't have any problems there. So what are we going to have to do? Again, notice this is a product. So I'm going to take the derivative of x times e to the 2x plus x times the derivative of e to the 2x. That's the product rule. Now the derivative of x obviously is easy as 1. What do I have to use here to find the derivative of e to the 2x? Now that's chain rule, right? Chain rule. I got e to the u. E to the u is the outer function. U equal 2x is the inner function. The derivative of e to the u is e to the u times what? The derivative of the inner function, which is 2. So 2e to the 2x. And so this becomes 1 times e to the 2x plus 2x e to the 2x. Again, I can factor. E to the 2x is common to both, leaving me 1 plus 2x. Okay? So, again, this is never undefined. There's no value of x that I can't get a real number as an output for my derivative. The question is then, when is it equal to 0? Well, e to the 2x is always greater than 0. This is always greater than 0. It's never going to be 0. But 1 plus 2x will be 0, right, when x is equal to what? Negative 1/2. Right? 1 plus 2x is equal to 0 when x is negative 1/2. And so that right there is our only critical point. Okay, in the next video we'll talk about the relationship between these critical points and finding max and mins on a closed interval.